Hey everybody, thanks for turning up. It's a great crowd. So where do I go? It'll work.
Oops.
Oop, no, not that one. All right. Yes, so I'm actually wearing a Hawaiian t-shirt because I got out of Yorkshire and the drizzle, and I went to Hawaii for grad school. Unfortunately, I didn't get to go recently to this Giant Magellan Telescope science meeting, which Raquel went to. So I'm going to talk about how you actually gather the data that breaks open the mysteries of the universe. And the key thing here is that we've always been striving to see further, to gather. All right. Ooh, okay. All right. Ooh. All right. Striving to see further, gather data from fainter and fainter objects. When you see further, you look back in time. I build a lot of instruments, but I also do it to do cosmology, which is studying the shape, the age, the evolution of the universe. And so I'm very interested in this thing, the Giant Magellan Telescope, which we are a partner in. Anyway, so really what I'm going to tell you about is why we want to build bigger and why we want to search for new technology in order to facilitate all of this. Okay, so this is the first known picture of a telescope. So, if I can get it right, Giovanni Battista della Porta wrote a letter, and I don't know who he wrote a letter to, but it was August 1609, and it could have been Galileo, because in 1609, Galileo built that. So the first telescopes, though, were not built for astronomy. We were way too unimportant for that, but they were developed for the military. So you're on a boat and you want to know what the other boat is over there, you need a telescope. So, however, Galileo quickly repurposed the telescope idea, and he built one that was an inch in diameter. So it's a lot more than your eye can see, because your eye's only got a sort of 1/4 of an inch aperture on it. So you definitely improved with a telescope. So that was pretty impressive. Took until 1671 for Newton to invent the reflecting telescope. So there's a mirror down the bottom of there. It's bigger. So that's kind of cool. And we've been kind of trying to build bigger and bigger reflecting telescopes ever since. The biggest refracting telescopes, like Galileo built, kind of max out at about that kind of size. The glass, is very hard to make the glass much bigger than that. So you build reflectors. And that is the Hobby Eberly telescope out in West Texas, which is our premier telescope. And that has an 11-meter scale mirror made out of 91 individual reflective segments. So the largest telescopes now, which are 10 meters, 33 feet in size, have 160,000 times the light gathering power of Galileo's first telescope. So we've improved on that. That's why we build bigger telescopes, because with a lot more collecting area, we can see a lot fainter stuff. So this is the next generation. You've heard about the Giant Magellan Telescope, but there's also the 30-meter telescope, which is being developed by an international consortium led out of California. And then there's the European extremely large telescope, and that thing is 40 meters in diameter. And for scale, that's our Hobby Eberly telescope, which looks completely puny, as does a human, if you can actually even make out the human over on the right there. So these things are monsters. And it's interesting, like the Giant Magellan Telescope's got a different philosophy. Instead of building lots of small mirrors together, it's actually only got 7 big petals. So I think actually this is a clever way to go, and I think it will be the first one on Sky. However, that is 3 million times the area of Galileo's telescope. So basically we keep striving to gather more and more light. So the next thing I'm going to talk about is detectors. Okay, you've gathered the light, what do you do with it? You're certainly not going to hang around the back of the European extremely large telescope with an eyepiece on trying to see things. So this is Galileo showing the Doge, how useful this would be in naval warfare, his telescope. Your eye has a 1% efficiency, so you only detect 1% of the light that falls on it. It's not bad, it works at night and stuff, it's pretty good. So photographic plates, that's kind of what we used, and we've learned how to do all kinds of things, like selecting particular cows that had eaten a particular type of grass for the gelatin that went into these. And that's a 200-inch, which is the largest telescope for a long time. And that guy there is actually on a gantry, so he can guide his exposure of this photographic plate, which would go on for hours, using an eyepiece so he could keep it centered. So when I started astronomy, I missed photographic plates, but we were still guiding by eye. So I spent many hours going like, oh no, left, left, right, left, right. So it's very, so I kind of saw the tail end of it. So that's about a 3% efficiency. So way, way better than the eye. And of course, also, you get a nice big area. So that was an amazing resource for us for a long time. Then there are charged coupled devices. There are other detectors in the infrared and things like this, but this is something that you actually are all familiar with because they're in your phones, right? So these were actually originally, they were supposed to be storage devices when they were first developed, but it turned out they were sensitive to light, so they weren't very good as storage devices. But they turned out to be an amazing detector. And they started off quite small, and almost as soon as the military declassified them, astronomers were all over them. And we actually were a conduit for them going into medical imaging. Every X-ray that's taken of you nowadays, more or less, is taken with a CCD. So they have a essentially perfect efficiency over a large portion of the optical band. And they also come quite big. On the side there, the one on the right-hand side is one of the biggest individual ones that's been made. And then what we do is we put them together in mosaics, and that whole array there, which is the dark energy camera, which is in Chile, is literally sort of 1.5 feet in diameter, which is quite amazing. So they also have to be cold because the one in your phone takes very short exposures, but we take long exposures. And if they're too warm, they generate a lot of spurious, what we call dark signal. Anyway, there's a lot of technology to make something like that work, obviously. So now at this point, if you take say, one of those CCDs and put it onto, say, our Hobby Eberly telescope, you have 16 million times what Galileo would have been able to detect with his eye when he first realized that the moons of Jupiter were kind of like going around, and that was a mini solar system. So this is an amazing resource. If you combine these, as people will be doing, with the extremely large telescopes, the next generation, 25 to 40 meter class, you're talking about 250 million times. So really, you can take light, you can detect incredibly faint things, but also you can dissect it and get more information than you can just from some image. So the next thing I'm going to talk about is spectrographs. And that's kind of where I make my bread and butter. I build telescopes. We just finished upgrading the Hobby Eberly telescope, but I build spectrographs. And so there's a prism dispersing light into a rainbow. That's basically one way of making a spectrograph, if you had some way to detect that spread. We also have things called diffraction gratings that do it as well. But William Herschel over there was the first to actually take a spectrum of a single star and demonstrate that he could see absorption lines in that spectrum that were indicative of the elements that were in the atmosphere of the star. He also detected infrared light, heat, for the first time. So behind here is actually a spectrum of the sun taken with a telescope at the European Southern Observatory, going all the way from the sort of deep violet out into the far red. And you see all of this structure in here, all of these sort of darker bands and sort of fainter bands, and all of those are due to atoms in the atmosphere of the sun that are actually absorbing the light that's trying to get out. So there's a huge amount of information. We can tell exactly how much carbon and oxygen and other things the sun has. So that's called a high-resolution spectrum. But what I do is I build things that are actually much more moderate in what they try to do with the light, but they try and look at incredibly faint objects on the other side of the universe. So I'm going to talk now about what we're doing specifically in Texas after that intro. And so here is a schematic of the Hobby Eberly telescope. It's actually very hard to take a picture of it, so it's kind of better to have a diagram. So this is what we have been doing in the last decade, is upgrading this telescope and adding this instrument that we call VIRUS. I won't actually unpack the acronym because I just love the name. But basically, VIRUS is meant to sort of be a replicated instrument. And that's very different from what we normally do. We normally build one, we go and do something with it, and then we have another idea and we go and build something completely different. Instead, we get a huge amount of power out of this by mating this to the 10-meter Hobby Eberly telescope, and the green kind of cords you see coming down are actually 35,000 optical fibers going from the focal surface of the telescope up to the top there into a distribution of spectrographs that are in these kind of enclosures on the side, which, since we're in Texas, we call saddlebags. So this is far and away the most powerful spectrograph telescope combination ever built. And at this point, we're past halfway deploying this, and it's already far and away the most powerful spectrograph telescope combination ever built. So a little bit about spectrographs. So what Herschel did was he took the light of a single star and he used a dispersing element, in his case a prism, but you can use a thing called diffraction grating. There's a reflective one there. It spreads it out into a light, into a spectrum, and you focus it onto a detector. So that, for a long period of time, that's what astronomers did. They took a spectrum of a single object at a time. Now, we want to get information more rapidly. The whole point of VIRUS is, and the Hobby AoT telescope combination is to take spectra of about 2 million objects in a few years' time. So what we have is what's called an integral field spectrograph. And what it does is it actually breaks up the image of the sky and focuses those little bits that it's broken up into fibers, optical fibers. And optical fibers are great because what you put in one end comes out the other. It can be 20 meters away or it can be across the ocean. And you then feed that into the spectrograph and line them up in a line, kind of like the slit in the slit spectrograph, and you get lots and lots of spectra. And when you've analyzed that, you can pull it back and you get a three-dimensional data cube. So basically you get a spectrum of everything that is in that image, but you've actually got all this physical information about it. Okay. So how do we do that? We make these fiber cables. So we've been doing this in collaboration with an institute outside of Berlin. And for each of our spectrograph units, we have one of these fiber cables. Each one has 448 fibers. They're 20 meters long. And in the end, we've basically purchased and put into these cables 400 miles of fiber. So we're actually in the telecom level of fiber purchasing. So they're arrayed out in this little array here. And you can see the end point there. And there's a cable kind of wound up there on the right. Happy to talk to anybody who's interested about the technology later. So we've arrayed, as I said, the spectrographs in these saddlebags. That's what they actually look like. They're two massive sort of clean rooms that sit either side of the mirror of the telescope. And here we've got a few images of us actually sort of deploying these. So each one of these spectrographs, just a single channel, and there's two in each of these, a few years ago would have been a really powerful instrument in its own right. And in fact, a decade ago, we built a prototype of it, and we've been using it on a 107-inch telescope for a decade, and it's still one of the most powerful instruments that we have. So here we're going to have 156 times that on a telescope that's nearly 5 times bigger. So here we have 8 of the units waiting installation, and we sort of rig them up and lift them in, and then we install them into their place, into their slots in their enclosure, in their saddlebag. It's actually quite simple. It takes about an hour to install one at this point. We've done it so many times. So this is kind of going back to the power of this instrument. So 78 of these units, 35,000 spectra simultaneously. We make these data cubes, so we can dissect it in many ways. But what we're actually doing for this project is, the whole motivation is called the Hobby AoT Telescope Dark Energy Experiment, and we need to discover the emission lines from individual galaxies that are located 11 billion light years away, so 11 billion years back in time. And we're going to map out their positions in a volume of space that's bigger than any map that's ever been made by humans. And so each one of these little blips here is light that was emitted by hydrogen atoms in a star-forming galaxy 11 billion years ago or so. And there are 300,000 spectra taken every hour with VIRUS when it ultimately is going. So we're about half that right now. And so each one of these blips represents a single spectral element. And sometimes there's an object there, but often there isn't. And we'll have 130 million spectral elements every hour. This is the area that we're going to survey. It's actually so big you can actually sort of see it on the sky. We're going to figure out what's inside the Big Dipper, maybe. We're going to take 4,000 observations over 4 years with the combination of VIRUS on the Hobby AoT telescope. So that's 400 million spectra with 170 billion spectral elements. Hence my moniker. I'll be a spectro billionaire. So we will discover in this data set 2 million galaxies. Now, that's a lot of galaxies, and it's going to be a very big volume of space, and they're located a long way back in time. And we'll use this to figure out how fast the universe is expanding back then, which will actually, hopefully, tell us a lot about the dark energy that accelerates the universe, or maybe doesn't exist. However, there are there are all of these 170 billion spectral elements in the data set, and there are only 2 million galaxies hiding in that. So there's only one galaxy per 100,000 spectral elements. So finding them and characterizing them, making sure they're real, is a huge problem of big data astronomy. And we have people at the back nodding who have been involved doing this from the early days of it. And it's a very exciting tool. It's a very, very powerful instrument. You don't need to know ahead of time what you are looking for, because you just take a spectrum of the sky and see what's there. So there'll be all kinds of interesting things, like the very oldest stars in our galaxies hiding in our galaxy hiding in this data set as well. So anyway, hopefully I gave you a flavor of why we do this and what we hope to do with the next generation of instruments. So thanks very much for your attention.
All right, we'll do some Q&A. The way this will work is if you have a question, raise your hand. We'll call on you. You'll ask your question. Hopefully one of us will remember to repeat the question, and then you will answer it. So let me see. Any questions from the audience? Yes, up here in front.
So storing all this information, what's the data footprint?
Yeah, actually, compared to, say, that array of imaging chips, the CCDs that I showed early on, it's actually not bad. Oh, yeah, sorry. So, you're right. Repeat the question. So, what is the data storage requirement for a data set like this? Very good question. So, so compared to what you see from the imager, which actually probably takes an image every few minutes, it's actually not that great. In the end, after 4 years, we expect to have about 10 petabytes of data, including the reduced products. And what happens is this data, it hits the disk in West Texas at the Hobby Abbey Telescope, and within about 10 minutes, it gets automatically transferred to the Texas Advanced Computing Center up in the Pickle Research Center in North Austin. And basically, they have an infinite amount of disk space and an infinite amount of computing power as far as we're concerned. And basically, the data gets reduced in a fairly automatic fashion. And then the fun comes of like squinting at it and trying to figure out, have you done it quite right? But the actual data handling requirements are actually relatively modest compared to big data in astronomy nowadays. Yeah.
All right, let's take another question. How about you right there?
How would you classify galaxies out of this data set? Is it like thousands and thousands of undergrad?
So the question is, how do we classify these galaxies that we find, and is it a whole load of undergraduates squinting at them? That's remarkably close to reality, but at least early on. So as the first data kind of came in, there was a lot of squinting, a lot of like, is that real? No, it isn't. Is that real? No, it isn't. But now it's a lot more automated. So basically, there are algorithms that go into the data set and they find basically things that they think are real against the noise. And the good thing is actually the flip side of having so few objects compared to just everything else is that we get an incredible measurement of the sky and hence the amount of noise. So we have a very good expectation of what to find. But the reality is that a lot of this was looked at by undergraduates and graduate students and professors and anybody who could rope in. And even a bit out on the big world of the internet, with sort of through crowdsourcing. And we've been using that to train AI algorithms. And there's a group in University of Tokyo who are part of this project. This project, I should say, has institutions in Germany, in the UK, the US, and in Japan associated with it. So they've actually jumped onto this. And they actually have an algorithm trained by the subset, well, basically the superset of everybody who's looked at one and said, is that real? I'm not sure that necessarily is better than trying to figure out if it's a real thing, but we're definitely doing that, and so that's one of the things. So, virtual undergraduates.
All right. Let's see. Any up top? I don't see any up top. We'll do 2 more questions. You first, sir.
Great idea. So why did we select the survey error? Other than it goes through the Big Dipper and everybody knows it, and even I can spot that constellation. But no, actually the reason is that the Hobby Abbey Telescope, the way it's designed, it doesn't move around in all axes. If you want to look over here, you pick it up and you turn it around and you put it down, and then you use this tracker to move across. And that ended up allowing us to build this telescope for about 20% of the cost of the other 10-meter telescopes. So I tell my European colleagues that we built it for the value-added tax on their telescope. And so basically that shortcoming means that actually it's more efficient to observe in the north, where the sky actually is going past slower. If you think everything's rotating around the pole star due to, it's not rotating, we're rotating, but basically it moves slower up there, so we can actually get longer integration times up there. So that's why it's up north. I think you've been putting your hand up.
Sorry, I'm laughing at myself. I'll tell you after this last question right up here.
Okay.
It's two questions, actually. It's a 3D arrangement where you spread out the spectrum and then you create a 3D image and slice that up. Is that the order in which it is done, or are they both separated out simultaneously?
Yes, so the question is, do we put the data into sort of a cube and then slice it up, kind of as the cartoon showed? You can do that, but actually we tend to stay closer to the data. So every pixel in the spectrum on a given detector, we know where that came from on the sky and what its wavelength is associated with in the spectrum. And so we actually put this together in software so we don't have to manipulate the data, because anytime you kind of turn it into a cube, you actually end up averaging it in some ways, and we don't really want to touch the data if we can help it. So that's the way we do it.
Perfect. So question 2, how do I get on your data?
So you can. There's actually guys at the back here. You can just come up and talk to me afterwards.
All right, with that, another round of applause for Dr. Gary Hill.